class. This lecture will be on Unit 16, Inductance in AC Circuits. Inductance is one of the three major types of loads or components found in AC circuits. The first one that we've been dealing with throughout this class was resistance, or a resistor. The new one we're going to start looking into is inductance. One of the major effects that inductance has on a circuit is that it causes the current to lag the voltage in regards to phase. Now remember, in a purely resistive circuit, if we were to measure the voltage over time as an AC sine wave, like this, and then also graph the current, like this, they are in phase with one another. And when I mean in phase, I mean they are in time with one another. So they both start at zero, they both peak at the same time, they both hit their zero crossing at the same time, they both hit their maximum negative value at the same time. So this is what we would say is in phase. With an inductor, that will no longer happen. We'll actually find that the current will lag the voltage in regards to phase. Another thing that inductance introduces into a circuit is something called impedance. And then impedance, that we'll find later on, is a combination of resistance and inductance. So a new circuit value, inductance, symbolized by the letter L, as units of henries, symbolized by the letter H. Technically, inductance is present in all alternating current circuits, even if an inductor is not in circuit. This is due to the fact that AC circuits have a changing magnetic field. However, this inductance is usually so small that it can typically be ignored for circuit analysis. However, when we place an actual coil of wire in a circuit, that inductance can no longer be ignored. So if we have any type of circuit and we put some type of coiled wire in that circuit, that coil is going to introduce an inductance in a circuit. And then so major factors of inductance. First is that when magnetic lines of flux cut through a coil, a voltage is induced in the coil. Magnetic lines of flux cut through a coil, a voltage is induced in the coil. That is that law of magnetic induction, one of the most important laws in electricity. Second, an induced voltage is always opposite in polarity to the applied voltage. Typically we call this a counter EMF or back EMF. So in a circuit, we have an applied voltage at our source, so this is some voltage in volts AC. It's going to have a direction. And then we will have an induced voltage from our inductor that is in the opposite direction, and this is our counter EMF. It always opposite in polarity to the applied voltage. And finally, number 3, the amount of induced voltage is proportional to the rate of change in current. So the amount of induced voltage is proportional to the rate of change of current. So that means if the rate of change of our current in our circuit changes faster, this counter EMF will be greater. And finally, our fourth major factor of inductance. Number 4 is that an inductor opposes a change in current. So an inductor, if we try to change the current through that inductor, it does not like that. It opposes that change. So if we're trying to put a current in this direction, it's not going to want a current in this direction. So it's going to oppose that current flow. And then one more rule, important rule. An inductor stores energy in a magnetic field. Remember, when we have an inductor and we have current flow through that inductor, a magnetic field appears around the conductor. And an inductor stores energy within that magnetic field. So if we have an alternating current, or excuse me, an alternating voltage, E, we'll find that in an AC circuit, the voltage is constantly changing polarity back and forth. Here, we have a positive polarity, then it goes to a negative polarity, and it just keeps going. Remember, here in the USA at 60 hertz, so 60 times in 1 second. That means that the voltage in an inductor is constantly being induced in an inductor coil. And that imposes the applied voltage. So if I have a circuit with some applied voltage, AC voltage, and an inductor like this, I have an applied voltage from the source. And I'm going to have a counter voltage or a counter EMF from the inductor. This induced voltage right here is 180 degrees out of phase with the applied voltage. So if I was to graph this counter voltage, it's going to be 180 degrees out of phase with the applied voltage. So the applied voltage is always opposite in polarity to the counter voltage induced by the inductor. And so whenever we have something opposing our applied voltage or applied current, we're going to give that something with units of ohms. And so this leads to an important circuit value called inductive reactance. Once again, notice we have an applied voltage, and when we have an inductor in a circuit, like this, that inductor creates a counter voltage. Now remember, previous circuits, resistive circuits, the value that we had for opposition to voltage and current was resistance. Technically, inductive reactance isn't the same thing as resistance, but like resistance, it opposes our applied voltage or applied current. And so we will give that units of ohms, same as resistance. So inductive reactance, which is created by the induced voltage of an inductor is the current limiting property of an inductor. So inductive reactance symbolized by the letter X sub L as units of ohms. Omega, same as resistance. In a circuit with an inductor, so we have an inductor with some value L in henries. It's also going to have an appropriate value of inductive reactance. This is found through the formula 2 times pi times F times L, where F, remember, was your frequency in hertz, and L is the inductance in henries. So F is your frequency of the circuit in hertz, and L was the inductance of the inductor with units of henries. And now, since XL, inductive reactance, has units of ohms, it can be used in Ohm's law. So let's do an example. Let's imagine we have a circuit with 120 volts AC, and the frequency, so this is our total voltage, and the frequency is 60 hertz. Now on the homework, you might have some problems where they don't give the frequency of the circuit. If it's not given, please always assume 60 hertz, since here in America, that's what we use. And then finally, the inductors are going to have an inductance of 0.8 henries, and we want to find what is the inductive reactance. So the inductive reactance is 2 times pi times the frequency times the inductance. So XL will be 2 pi times the frequency of 60 hertz times an inductance of 0.8 henries. And that'll give us a value of 302 ohms. And now we can also actually find the current in the circuit as well through Ohm's law. Now remember, the Ohm's law that we dealt with before was E equals I times R. However, if we want to make this a little more general, we just use the units. So units of volts is equal to units of amps times units of ohms. So if I have a total circuit voltage here of ET, ET has units of volts. I'm trying to find the current of the circuit IT. Well, what do I put here? I can't put R resistance because I don't have a resistor in the circuit. However, I do have inductive reactance, and inductive reactance has units of ohms. So I can put X of L right here. And that means that our current, IT, would be ET divided by X of L. So that would be 120 volts AC divided by 302 ohms. And that's going to give us a value of 0.398 amps. Okay, so let's do another circuit. And let's say that we have an inductive reactance of 500 ohms, and we want to know what is the inductance. Well, we know that inductive reactance, XL, is equal to 2 pi times the frequency times L. We're trying to find L, so we're going to algebraically solve for it in this equation. I'm going to divide each side by 2 pi times the frequency. That cancels that all out, and finally I get L equals the inductive reactance divided by 2 pi times the frequency. I'm also going to add on parentheses here. So when you enter it into your calculator, please make sure you put these parentheses here so that we group everything together in this denominator. So the inductance in this case is going to be 500 divided by 2 pi times 60. On your calculator, how would you put this in? You would do 500, hit the divide sign, hit the left parenthesis, do 2 times pi times 60, and then close it off with the left parenthesis. The value that you'll get for inductance is going to be 1.33 henries. Okay, so different symbols for inductor that you'll see. The one that I've been using is like this. You also see one like this. The one without the 2 lines is an air core inductor. The one with 2 lines would be an iron core inductor. In common everyday use, you pretty much always use an iron core inductor. However, this is just quicker to draw, so I'm just going to use this one whenever I'm drawing circuits. And so now, what if we want to put multiple inductors in the circuit? So let's say I put 3 inductors in series, L1, L2 and L3. L1 is 0.5 henries, L2 is 1 henry, and the L3 is 2 henries, and I want to know what is the total inductance of the circuit. It's pretty easy. It's the same, behaves the same way as resistors, so that means that the total inductance would simply be the simple sum of each inductor. So the total inductance here would be 0.5 henries for inductor 1, 1 henry for inductor 2, and 2 henries for inductor 3. That would give us a total inductance for the circuit of 3.5 henries. This is also true for the inductive reactance. So if we had an inductive reactance of 10 ohms for inductor 1, inductive reactance of 20 ohms for inductor 2 first, and then an inductive reactance for inductor 3 of 40 ohms. That means the total inductive reactance is simply the sum of each one. So XLT, the total inductive reactance, is XL1 plus XL2 plus XL3, which is going to be 10 ohms plus 20 ohms plus 40 ohms, which gives us a total of 70 ohms of inductive reactance for the circuit. Next, let's put inductors in parallel. And as you might guess, it is exactly the same as it was with resistors. So if I have three inductors in parallel like this, L1 is 0.5 henries, L2 is 1 henry, and L3 is 2 henries, like this. We want to know what is the total inductance of the circuit. It's going to be the reciprocal of the sum of the reciprocals of each inductor, or 1 divided by L1 plus 1 divided by L2 plus 1 divided by L3. Remember, on this formula, that means that the total inductance should be less than the smallest inductor, so we know it has to be less than 0.5. And that gives us a total inductance of the circuit of 0.286 henries. The same is also true for the inductive reactance. So the total inductive reactance of a parallel circuit is 1 divided by XL1 plus 1 divided by XL2 plus 1 divided by XL3. So this will have inductive reactance associated with it, same here, and same here. And once again, if the frequency isn't given, you always assume the frequency is 60 hertz. So now let's look at how voltage and current behave in a purely inductive circuit. circuit, purely resisted, we graph voltage and current. It looks something like this. Remember, voltage and current in a purely resistive circuit are in phase. However, this is not true in a purely inductive circuit. In a purely inductive circuit, the current lags the voltage by 90 degrees. So in a purely inductive circuit, the current lags the voltage by 90 degrees. So what does that mean when we graph voltage and current over time? We're still going to keep the voltage the same. Starts at 0, goes through a full sine wave, but the current is going to look different. Current is going to look something like this. And so when I say the current lags the voltage by 90 degrees, I took a look at 90 degrees, which is right here. So we notice that t equals 0, time starts at 0. The voltage starts at 0. However, the current doesn't start at 0 until 90 degrees of time later. So this seems like an impossible condition. How can we have a maximum amount of voltage but zero current? That makes no sense, right? If we have a complete circuit and we have an applied voltage, we should have current. But at this specific point in time, in a purely inductive circuit, when we have a maximum amount of voltage, we actually have zero current flow in the circuit. However, there's also a relationship between the current and the induced voltage. Remember, when we have an inductor in a circuit, there's also an induced voltage, or a counter voltage. And remember that our induced voltage is 180 degrees out of phase with our applied voltage. So it's going to look something like this. And so the current in our alternating current within an inductor is entirely based, which I have to try to keep the color code right here, so I'm going to have a current I in the circuit, I'm going to have an applied voltage in this direction, E, and I'm going to have the counter voltage in this direction in the inductor. And so the value of this current is based entirely on the value of our counter voltage. And it's based on the rate of change of the counter voltage. So when I mean rate of change, I mean the slope. So each of these graphs has some slope associated with it. So if we're looking at the counter voltage, the counter EMF, the green graph right here, this has a slope associated with it as I go along with it. And so you notice here at the top, or the maximum, the slope has a 0 degree slope. And as I keep going this way, the slope gets greater and greater and greater and greater. So let's follow this. So here I have a maximum slope, and the slope is in the negative direction. So I'm going to have a maximum negative current. As I keep going like this, I hit this point right here. This has zero slope with it. At zero slope of the induced voltage, I have zero current. As I keep going, keep going, keep going, keep going right here, I have about the maximum slope I will attain on my induced voltage. And lo and behold, I hit the maximum amount of current. I keep going, keep going, I keep going. I hit a zero I have a zero slope on my induced voltage, and I have zero current in the circuit. And so that is how current behaves in a purely inductive circuit. Its value is based on the rate of change of the induced voltage or counter voltage from the inductor. So you guys didn't realize it, but what you were actually doing with this slope and correlating the slope of the EMF and the current, that was actually differential calculus right there. So you guys all just did a little bit of calculus. So enough about voltage and current in the circuit. Now let's look at how power behaves in a purely inductive circuit. Remember, in a purely resistive circuit, the true power of watts is equal to the product of voltage and current. So resisted, the true power, P, is simply the product of your current and your voltage. And remember, we define true power as power that can be converted to some other useful form. However, in a purely inductive circuit, no true power is created at all. All of the power goes into creating the magnetic field of the inductor. And when that magnetic field collapses, the power is then given back to the circuit. So in a purely inductive circuit, all the power from voltage and current goes into creating a magnetic field around the inductor. And then that magnetic field, when it collapses, puts power back into the circuit. But we cannot actually extract any of that power. And so that means that the true power P, as an inductive circuit, would be 0 watts. And so that leads us to a general formula for finding true power. The true power P is equal to the voltage times your current times cosine of angle theta. So we all know what P means, true power. We know E is voltage, I is current. What is angle theta in relationship to an electric circuit? Remember before, when we talked about angle theta, we meant some angle in a triangle. Well, a circuit is not a triangle, is a physical thing. And so angle theta in an electric circuit is the phase difference between the voltage and current in the circuit. Now remember, for a purely inductive circuit, the phase difference between voltage and current is 90 degrees. So let's imagine we have some applied voltage of, I don't know, 120 volts. We have a current flow through the circuit of 10 amps, And we're in a purely inductive circuit. The angle theta between voltage and current is going to be 90 degrees. So let's look at that mathematically. So the true power P of the circuit would be 120 volts, 10 amps of current, times cosine of 90 degrees. And put that on your calculator. And I'm going to get 0. So 0 watts in this circuit. However, we still do have power. Remember that an inductor stores energy in a magnetic field, and power is simply energy over time. So we have a constantly changing magnetic field in this inductor. So we have essentially a constantly changing power. So that leads us to a new type of power in our circuits. And that power is called reactive power. So even though an inductor doesn't emit true power, any type of true power, remember we cannot actually extract any power from an inductor. It does emit a power as a product of current and voltage, and this new type of power is called reactive power. Reactive power is symbolized by VARS L. VAR stands for volt amps reactive. So in general, all types of power are always going to be volts times amps. Okay? Now the R stands for the fact that this is reactive power, not true power. And then the L stands for the fact that we're using an inductor in the circuit. It also has units of VARs as well. So this is the only case where the symbol, the quantity, and the units are exactly the same. Our equation for VARs in an inductor is EL times IL. So EL, the voltage drop across the inductor, and IL, the current through the inductor. And so at this simple circuit right here, we would have the full voltage across the inductor, and we would also have, since this is a series circuit, the current's got to be the same everywhere, we would also have 10 amps through the inductor. And so what would be our reactive power through the inductor? It's going to be EL times IL. So EL is 120 volts times 10 amps. That's going to give us 1,200 bars of reactive power for our inductor. So it has 1,200 reactive bars, or reactive power, but it has 0 true power. And so, let's finish this off by solving a simple circuit. With only an inductor in it. here's our circuit. Let's solve for the rest of the circuit values. This is just a simple series circuit. So the first thing we probably want to do is find the total current. But we cannot find that yet because the total current would be the total voltage divided by XL, and we do not have XL. Remember, in general, for Ohm's law, volts is equal to amps times ohms. So the current, which has units of amps, would be volts divided by ohms. Remember, X of L has units of ohms. So next, let's try to find X of L. X of L is 2 pi times your frequency times your inductance. So this is 2 pi times 60 hertz times an inductance of 0.5 henries. And that gives us an inductive reactance of 188.5 ohms. Here, E sub L is easy. We have a simple circuit, which is one component, so the applied voltage would have to equal the voltage drop across the inductor. So we'd have 100 volts for the voltage drop across the inductor, E sub L. Next, the total current, ET divided by XL. So 100 volts divided by 188.5 ohms. Gives me 0.531 amps. This is a simple series circuit, so the current is the same everywhere. So I'm also going to have 0.531 amps through the inductor. And then finally, let's find the reactive power of the circuit, part L. That's going to be EL times IL. Once again, if we were going to use Watt's law, so before when we saw Watt's law, it was P equals I times E. Power in general, no matter what type it is always going to be amps times volts, always. So if we're looking for the power, or in this case the reactive power to the inductor, it's got to be the volts times amps of the inductor. So the volts for the inductor is EL, and our amps to the inductor is IL. So this is going to be 100 volts and 0.531 amps. That's going to give me 53.1 bars of reactive power. And that concludes our lecture on Unit 16, Inductive and AC Circuits. I don't know about you, but this is incredibly awkward right now. I really wish you guys were here in class, but we'll get through this. It's going to be awkward and weird for me, and I'm sure it's going to be awkward and weird for you, but we'll get through the rest of the semester. Thank you for your patience.